Hi, welcome to everyone. I'd like to say it's an honor to be here. I'm a present. My name is Lucas Salustiano Mendes, and at present now, I study about the theoretical analysis of the exercise of a 7x1 and pumped power combiner. I'm a postgraduation student of Nuclear and Energy Research Institute in the University of São Paulo. For this presentation, I follow this outline. I will begin with introduction about power combiners. Then, I will talk about the theoretical model with a brief description of the coupling mode theory and coupling coefficient. Then, I will present the results and finally a conclusion about the main topics of this work presentation. Optical fibers are widely used in communication, instrumentation, fiber laser, and numerous other applications. Regarding the fiber laser, their attractive properties including excellent beam quality at output power, compactness, high transmissive size, and low maintenance, have facilitated its extensive application in the industry, medicine, research, and other areas. The development of fiber device has enabled the construction of all fiber configuration, where all devices made of fiber. So in this, the light remains in the waveguide to output laser, reducing the loss and maintaining the beam optical quality. The coupling method of the pump light in the active fiber contributes directly with the transmissive size, and the most employed coupled device is the fiber combiner. Fiber combiner presents a typed bundle of input fiber which are typed and spliced to output fiber based on typed fiber bundle method (TFB). Therefore, a high-power N/1 combiner can be designed using TFB method in n input multimode fiber and one output fiber with similar characteristics. The model considers what? The pump fiber of a 7x1 fiber combiner, which each input fiber has circular symmetry and that in the taper region, the core radius has a gradual decrease along the taper. To ensure that no power leakage in the taper from the core to the fiber cladding, the diabatic criteria must be attained. In this criteria, the radioaxial variation must be less than ratio between the core radius and the length between two reflections, called TP. Based on this information and with some algebraic development, we can find a relationship to minimal taper length based on fiber parameters, where A1 and A2 are the initial and final radius of the fiber and NA is the numerical aperture. Additionally, to avoid significant loss, the beam brightness is proportional to transmitted optical power and should be preserved. The brightness ratio parameter, BR, is a design parameter that must be bigger than 1 to avoid significant losses in the device, where Dout and De were the fiber final and initial diameter, M is the combiner input fiber, and Na is the numerical aperture. The coupled mode theory is an efficient method for obtaining quantitative information about the irregular waveguides. In order to obtain the coupled mode equation, the effect of perturbation have to be included, assuming that the unperturbed field modes remains unchanged. Therefore, consider the wave equation, where R is the fiber radius, Z is the axial length, M is the refractive index, Q is the free space propagation constant, and finally Pc is the propagation field. The behavior of the field in the taper can be described by the coupled mode theory. So, this means that the field at any point is expressed as a superposition of normal modes phi, where Cn is the modal coefficient expansion and beta z is the propagation constant. Applying this solution to the wave equation, one can obtain the differential equation below. Its solutions are known. They are: for the core modes, where An E is the magnitude of field and Jn is the first kind Bessel function. And this, the cladding solution, where Kn is the modified Bessel function. In the fiber tapers, all modes are coupled with each other, and the coupled coefficients are not independent. So, the coupled coefficient satisfies this equation, where R is the modal coupled coefficient at the boundary between the core and the cladding. Thus, considering the fiber taper in the power combiner with a step refractive index and large core radius, it is possible to describe the modal coupled coefficient as, where Uni and Umi are the modal radial propagation constant. Note that the modal coupling coefficients relate the modes 2 by 2. In this way, for each propagating mode there is a sum of the coupling coefficients of this mode with each other. One can be said that the modal coupling coefficient has a direct dependence with the first derivative of taper radius, and also has an inverse relationship with the radius fiber. In this work, three types of taper shape were studied: one linear, inverse square, and raised cosine, in order to study the performance of the loss coefficient of each one of them. Applying the taper shape equation in the modal coupling coefficients and finally in this differential equation, one can obtain the solution of the expansor coefficient or loss coefficients. Finally, the expansion coefficients can be used to calculate the power lost or modal power lost. And finally, this equation can be used to calculate the F size or modal F size. The present results consider a 7x1 power combiner with input fiber width 200-220 micrometer and .22 numerical aperture, and output fiber width ratio 400-440 micrometer and .46 numerical aperture. It was considered the pump power in each pump input fiber is the same. The fiber bundle was tapered and it has been all fused together. The multimode fibers, like the input fibers of power combiner, support tens of thousands propagation modes, but in this study only two low-order modes are studied. They are the main mode LP01 and LP11. Additionally, six higher-order modes are studied too. They are LP17, LP08, LP68, LP310, LP1010, and LP115. Finally, a MATLAB code using finite difference method was implemented to calculate the modal size from a taper fiber to a common fiber as a function of the taper length and shape. So, the modal coupling coefficient and phase constants were stored in a triangular 8x8 matrix, and the simulation was carried out for taper lengths from 1 mm to 20 mm with 1 mm steps. The results obtained were: to the linear taper shape, the results have present that the modal F size grows rapidly with the increase of the taper length, saturing at 13 mm with F size close to 97.5 approximately. One can see that the high-order modes are severely impacted by the taper size. Differently, low-order modes are little affected. To the raised cosine taper shape, the graphics have behavior similar to the linear taper shape, but their size is very small to short taper length. The saturing is about the 16 mm with F size close to 95 approximately. And finally, the inverse square taper shape. The graphic has a behavior similar to the raised cosine taper shape, with a size very small to the short taper length and saturated about the 16 mm with a size close to 95 approximately. Observing the graph of the first derivative of the radius along the taper, and knowing that it is directly proportional to the modal loss power, one can understand why the linear taper performance is better than the others. In the linear taper shape, the first derivative of the radius is a constant, and has a smaller magnitude than the first derivative of raised cosine and inverse square. The letters vary along the taper, and as can be seen in this circumstance of this study, the taper raised cosine presents the greatest variation of the first derivative, and consequently the greatest losses. The results indicate that if the fiber combiners undergo soft and adiabatic tapering and present only smooth changes in the radius, the fiber will present small losses. The simulation shows that the linear taper shape presents the best performance, and the raised cosine the worst one. Furthermore, the impact of first derivative is an excellent parameter to realize the taper loss and consequently the size. The linear taper reached 95% of size at 6 mm, while the inverse square and the raised cosine reached that mark at 16 mm. Finally, the results showed that high efficiency end-pumped combiner with F size about 95% can be designed with a small tapering relation and taper length shorter than 10 mm. So that's it. Thank you for watching.